It happened on a Tuesday afternoon in early May, in a stretch of wild mountain terrain most people have never heard of and couldn't find on a map without help. The Wenatchee Mountains of Washington state are not the kind of place where history tends to get made. They are rocky and steep and largely empty, draped in pine and snow well into spring, cut through by ridges that seem to exist mainly to remind you how small you are. And yet on May 2nd, in the middle of an otherwise unremarkable week, something touched down in those mountains that had never been recorded there before. Not once. Not in 75 years of careful record-keeping. A tornado. Not just any tornado, but one of the rarest and most visually arresting atmospheric phenomena in all of meteorology. A landspout spinning in the high mountain air above Kittitas County. Witnessed and filmed. Undeniable. The footage is extraordinary. A narrow white column extends from the base of a cumulus cloud, delicate at first glance, almost fragile looking, tapering toward the earth like a finger reaching down to test the temperature of something. But there is nothing fragile about it. What you're watching is a column of violently rotating air, a vortex generated not by the kind of supercell thunderstorm most people picture when they think of tornadoes, but by a completely different atmospheric process. One that is rarer, stranger, and in many ways more mysterious. The mountain ridges beneath it are grey-green in the spring light. The sky above is layered with cloud, and turning slowly in the space between them is something that had never been officially documented in this county in recorded history. To understand why this matters, you have to understand a little about how Washington state and tornadoes have generally gotten along over the years. The short answer is they mostly haven't. The Pacific Northwest sits on the wrong side of the continent for the kind of tornado production that defines the Central Plains. There is no tornado alley out here. There are no wall clouds churning over flat wheat fields in the late afternoon heat. The atmospheric setup that generates the most powerful twisters, warm moist air flowing north from the Gulf of Mexico colliding with cold dry air dropping down from Canada, that setup simply does not exist in this part of the world with any regularity. Western Washington in particular is sheltered by the Cascades, tucked behind a wall of mountains that wrings most of the moisture and instability out of the air long before it reaches the interior. But tornadoes do happen here. Rarely, yes. Weekly, usually. But they happen. In the lowlands west of the Cascades, waterspouts sometimes drift onshore and briefly qualify as tornadoes. Weak spin-ups occur occasionally in the Puget Sound basin during unusual storm patterns. East of the Cascades, where the terrain opens up and the atmosphere behaves a little more like the continental interior, there have been documented events scattered across the decades. The state of Washington has had verified tornadoes. They are part of the record. But Kittitas County, tucked between the eastern slopes of the Cascades and the beginning of the Columbia Plateau, had never produced one that made it into the official books. Not in the entire span of modern weather record-keeping, 75 years of nothing, and then May 2nd. Let us talk about what a landspout actually is, because it is not what most people imagine when they hear the word tornado. When the word tornado enters most people's minds, they think of a supercell thunderstorm, the kind that dominates storm chaser footage from Oklahoma and Kansas, a massive rotating complex of cloud and fury that can stretch dozens of miles across and persist for hours. These supercells have a rotating updraft called a mesocyclone, and it is from this large-scale rotation that a traditional tornado descends. The mesocyclone comes first. The tornado is, in a sense, a product of the storm's own internal engine. A landspout works almost in reverse. There is no mesocyclone. There is no supercell. Instead, what you need is a convective cloud, something like a vigorous cumulus tower or a weak thunderstorm growing upward rapidly. Below that cloud, at the surface, wind patterns create a thin horizontal layer of rotating air. When the rapidly rising updraft of the developing storm passes over that layer of rotation near the ground, it can pull that rotation upward, stretching it vertically and intensifying it the way a spinning figure skater accelerates when she pulls her arms in close to her body. The vortex tightens, the rotation speeds up. If conditions are just right, the column connects all the way from the cloud base to the surface, and a landspout is born. The result looks like a classic tornado, and by meteorological definition it is one. A column of rotating air in contact with both the ground and a cloud. But its origin is fundamentally different. Landspouts tend to be weaker than their supercell cousins. They tend to be shorter-lived. They can appear quickly and disappear just as quickly, sometimes before storm spotters even have time to report them. And because they often form under skies that look relatively benign by tornado standards, they can be genuinely surprising, appearing without the dramatic wall clouds and anvil-shaped thunderstorm tops that usually signal serious atmospheric violence. In the mountains, all of this becomes even more unusual. Terrain complicates everything in meteorology. Mountains create their own wind patterns, their own localized pressure gradients, their own interactions between surface and atmosphere. They generate mechanical turbulence. They force air upward and send it crashing back down. They create valleys that funnel and channel wind in ways that flat terrain never would. The interaction between all of these mountain-driven effects and the conditions required to generate a landspout is rare. It is the kind of event that requires a very specific set of atmospheric ingredients to align in a very specific way over a very specific piece of ground, and the odds against it happening in any given place on any given day are substantial. That it happened here, in the Wenatchee Mountains, on the 2nd of May, is the result of an extraordinary convergence of circumstances that meteorologists are still working to fully reconstruct and understand. Think for a moment about what it means to hold a record like this. Since 1950, the National Weather Service and its predecessor agencies have been systematically documenting tornado activity across the United States. The record is not perfect. In remote areas, especially mountainous ones, tornadoes almost certainly occurred before cameras were common and before anyone was watching. A tornado that touches down on a ridge at 6,000 feet elevation, far from roads and towns, may spin for several minutes, leave marks on the forest, and simply vanish without anyone ever knowing it happened. The absence of a record is not the same as the absence of an event. What the record tells us is not that no tornado has ever occurred in Kittitas County before May 2nd. What it tells us is that no tornado had ever been documented, witnessed, photographed, reported, and verified there before that date. That distinction matters. It means that the tornado on May 2nd was not simply rare in the meteorological sense. It was also rare in the human sense. It was observed. Someone was there, or someone had a camera in the right place at the right moment, and the evidence survived long enough to be submitted and studied and confirmed. In the history of atmospheric science, there are countless events that almost certainly happened and left no trace in the record because no one was watching. What makes the Kittitas County event remarkable is precisely that it was caught. The mountains revealed one of their secrets, and this time there was someone there to see it. The Wenatchee Mountains themselves are worth understanding as a place, because place matters in meteorology more than people often realize. These mountains form part of the eastern slope of the Cascade Range, a transition zone between the wet, maritime-influenced western side and the drier, more continental eastern side. The town of Wenatchee sits in the valley below, famous for its apple orchards and the Columbia River, but the mountains above it are a different world entirely, a landscape of exposed ridgelines, alpine meadows, and the kind of patchy snowpack that lingers into late spring. Elevation in this area runs from the valley floor at around 1,000 feet up to peaks approaching 8,000. That range of elevation in a relatively compact area creates enormous atmospheric variability. Temperature differences between the valley and the ridgetops can be dramatic. Wind patterns shift constantly as air drains downslope at night and pushes upslope during the day. When a weather system approaches from the west, the mountains force it to behave in complex ways that differ substantially from what models based on flat terrain would predict. For meteorologists studying the May 2nd event, understanding exactly what combination of wind shear, surface rotation, and convective development produced the landspout requires going back through the observational data with the full complexity of the terrain in mind. It is not a simple reconstruction. In the days following the event, the National Weather Service office responsible for the region began that reconstruction. They looked at surface observations from nearby stations. They examined upper-level wind data from radiosonde balloon launches. They reviewed radar data, looking for any signature of rotation associated with the storm cell that produced the tornado. They interviewed the person or people who witnessed and recorded the event. And ultimately, they reached the conclusion that yes, what was captured on camera was a genuine landspout tornado, meeting all the criteria required for official verification, and that it constituted the first tornado ever recorded in Kittitas County in the modern era of weather observation. The verification process for a tornado is more involved than many people realize. You cannot simply look at footage of a spinning vortex and call it confirmed. meteorologists have to establish that the vortex was in contact with the ground, that it was rotating, and that it was connected to a cloud base overhead. They look for evidence of surface interaction, dust or debris raised by the vortex near the ground, or in this case in a mountain environment, displacement of snow or soil or vegetation. They assess the overall atmospheric context to confirm that conditions were consistent with tornado formation. All of that analysis takes time, and it is a deliberate, careful process designed to ensure that the historical record remains as accurate as possible. When the verification came through, Kittitas County entered the record for the first time. A line of zeros in the tornado column of the database, stretching back through more than 7 decades, acquired its first number. It sounds like a small thing, the addition of a single data point to a database that already contains thousands of entries. But within that data point is an entire story, the story of a specific place, and a specific atmosphere and a specific moment when conditions aligned just so, and something emerged from the interaction that had never been documented there before. Weather records are, in their deepest sense, a form of memory. They encode what the atmosphere has done at specific places and specific times. They allow us to understand how unusual any given event is, how often similar events might recur, what the background rate of a phenomenon is in a particular region. Before May 2nd, the background rate of tornadoes in Kittitas County was, by the official record, 0. Now it is something greater than 0, and that shift, however small it might seem numerically, changes how meteorologists think about the atmospheric potential of this terrain. There is something almost philosophical about that. The mountains existed before the record. The atmosphere moved over them before anyone was watching. Events almost certainly occurred that left no lasting documentation, and yet in a formal sense, those events do not exist for science. What exists is what was observed and recorded. The first Kittitas County tornado exists because someone was there on May 2nd, and because the footage was credible, and because the meteorological analysis confirmed what the footage showed. Everything that might have happened before is, scientifically speaking, a ghost, real in some sense but unreachable by the methods we use to build knowledge. This is one of the reasons that the citizen science revolution in weather observation has been so valuable. Smartphones have turned millions of people into potential weather observers. Storm chasing has grown from a niche scientific pursuit into a broader cultural phenomenon. Dashcam footage, security cameras, trail cameras, drone footage, all of these technologies have expanded the network of eyes, watching the atmosphere in ways that would have been inconceivable 2 generations ago. Events that would once have gone completely unrecorded now find their way into databases and social media feeds, and ultimately into official assessments. The Kittitas County landspout might well have occurred before the age of ubiquitous cameras and simply disappeared into the mountain air without a trace. The fact that it was documented is itself a product of a specific technological and cultural moment. The broader context for an event like this is the question of atmospheric variability and what changes in the climate system might mean for extreme weather in places that have historically seen very little of it. Washington state is not exempt from the kinds of atmospheric changes that are reshaping weather patterns across North America. The jet stream that helps organize the large-scale weather patterns over the western United States has shown variability in recent decades. Atmospheric instability, the tendency of warm air near the surface to rise rapidly and generate powerful convective storms, can be influenced by changes in surface temperature. The specific conditions that produced the May 2nd landspout were almost certainly a product of natural variability rather than any direct climate signal, but the broader question of whether unusual atmospheric events might become less unusual over time in regions like the Pacific Northwest is one that scientists are actively exploring. The Cascade Range and the mountains to its east exist within a climate system that is changing. The snowpack that accumulates in the Wenatchee Mountains has shown variability over recent decades. The timing of snowmelt and the temperature contrast between mountain and valley during the transition from winter to spring influence the atmospheric dynamics of the region in ways that are not fully understood. When those dynamics produce something as rare as a landspout at high elevation in a county with no tornado history, it invites the question of whether this is simply an extreme example of natural rarity, the kind of thing that happens once in a long while purely by chance, or whether it is a signal of something shifting in the behavior of the atmosphere over this terrain. Scientists are careful about drawing strong conclusions from single events. One tornado in one county on one day is not evidence of a trend. The history of tornado occurrence in the Pacific Northwest is complicated by the same observational gaps that affect all remote and mountainous regions, events that happened but were never recorded, leaving artificial zeros in databases that might not reflect what the atmosphere was actually doing. Any meaningful analysis of whether tornado activity is changing in this region would require a much longer and more complete dataset than currently exists. What the Kittitas County event does, at minimum, is remind meteorologists that the atmosphere in the Pacific Northwest can do things that its historical record might suggest it cannot. There is also something worth noting about the sheer visual drama of a landspout in a mountain setting. The tornado footage that most people have seen comes from the Great Plains, from the flat and featureless terrain of Kansas and Oklahoma, where the sky dominates the landscape and a tornado moving across the horizon can be tracked for miles. Mountain tornadoes occupy a completely different visual register. The vortex appears against a background of jagged ridgelines and patchy cloud, framed by terrain that dwarfs it in one direction and is dwarfed by it in another. The scale references are confusing. The sense of displacement is acute. You're watching something that your visual vocabulary tells you belongs in one kind of landscape, appearing in an entirely different one, and the cognitive dissonance of that is part of what makes the footage so arresting. People who study tornadoes talk about the atmosphere as a physical system that is always, at some level, capable of surprise. No matter how well the models capture the general conditions required for tornado formation, no matter how thoroughly understood the basic physics are, there remain edge cases and outliers and events that push against the boundaries of what seems plausible. The May 2nd landspout in the Wenatchee Mountains is one of those events. It is not impossible, clearly, since it happened. But it sits at the extreme edge of the distribution of probable outcomes for that location and that type of atmospheric setup. It is the kind of thing that, if someone had predicted it in advance, would have seemed like an extraordinary longshot, and it happened anyway. That is one of the things the atmosphere seems to specialize in, happening anyway. The physical world does not consult our expectations before generating its extremes. It does not check the historical record to confirm that an event is within acceptable parameters before producing it. The atmosphere over Kittitas County on May 2nd simply did what the combination of terrain and temperature and wind and moisture made it capable of doing, and the result was something unprecedented in the documented history of that place. For the residents of the Wenatchee Valley and the surrounding mountains, the event is likely to remain a source of local fascination for years. First occurrences of extreme weather events tend to lodge in regional memory. People will remember where they were, what the sky looked like, what they heard about it afterward. The footage will circulate and recirculate, and the record, that long line of zeros finally broken by a single event, will stand as a reminder that the mountains where they live are capable of atmospheric behaviours that even the most experienced local observers had never seen. For meteorologists, the event is a data point and a case study and a prompt for further investigation. The specific conditions of May 2nd will be reconstructed and analysed and eventually written up in ways that contribute to the scientific understanding of tornado formation in complex terrain. The questions it raises about the atmospheric dynamics of the Eastern Cascades, about the role of terrain in generating surface rotation, about what combinations of ingredients can produce a landspout at high elevation, those questions will take time to work through. The answers, when they come, will be incremental and technical and probably not the stuff of dramatic headlines. But they will add something to the collective knowledge of how the atmosphere works in a specific and unusual place. And somewhere in the Wenatchee Mountains, the terrain where all of this happened sits largely unchanged. The ridgelines are the same. The valleys funnel wind the same way they did before May 2nd. The atmosphere moves over them, according to the same physical laws that govern the atmosphere everywhere. On another day, under another set of conditions, the ingredients might align again, or they might not for another 75 years or for another century. The record, now broken, offers no reliable prediction of when the next entry might be added. What it tells us is only that the possibility is real, that it was real before we knew it, and that the mountains have more to show us than we have yet been able to see. The landspout over Kittitas County lasted only a short time. It formed, it spun, it dissipated, as landspouts tend to do, leaving little behind except the footage and the questions and the newly updated record. In the grand catalogue of atmospheric events, it will occupy a small footnote, but in the specific history of this specific place, it is something else entirely. It is the first, and firsts, in science as in so many other things, carry a weight that no subsequent entry can quite replicate. The tornado that wasn't supposed to happen happened. The county that had no tornado history acquired one. And the mountains, vast and indifferent and full of secrets they have not yet chosen to share, remain as they have always been, waiting for the next time the atmosphere decides to do something no one expected. What happens next in a story like this is usually one of two things. Either the event gets absorbed into the local mythology and slowly fades, or it becomes the beginning of a deeper investigation into why it happened, and what it means for the place where it happened. The Kittitas County landspout is already doing both of those things simultaneously, which is exactly what you would expect from an event that sits at the intersection of the scientifically verifiable and the genuinely hard to explain. But the story of tornadoes in the Pacific Northwest, and what makes the May 2nd event so much more interesting than it first appears, actually starts much further back than the modern observational record. It starts with the question of what the atmosphere over the western United States is actually capable of, and how much of our understanding of that question is shaped by the incomplete and biased nature of the historical record itself. The National Weather Service database that stretches back to 1950 is an extraordinary scientific resource. It is also, if you look at it honestly, a document of observation rather than a document of events. What it records is not every tornado that occurred in the United States since 1950. What it records is every tornado that was observed, reported, and verified since 1950. Those are very different things, and the gap between them is largest precisely in the places where people are fewest and terrain is most complex. The Great Plains, where tornado observation density is highest, have a record that is close to complete. The Mountain West, where sparsely populated terrain stretches for hundreds of miles between observers, has a record full of holes. Researchers who have tried to quantify the size of those holes use a method called population-based correction. The basic idea is that tornado reports are not uniformly distributed across the landscape by meteorological factors alone. They are also distributed by human settlement patterns. More people means more observations means more reports. If you control for population density, you can get a rough sense of how many tornadoes the record is missing in low-density areas, compared to what the physics of the atmosphere would predict. The numbers, when you run them, are sobering. In some remote mountain regions of the western United States, the actual tornado frequency is probably several times higher than the reported frequency. Not because tornadoes are common there, they are still genuinely rare, but because the ones that do occur mostly happen without anyone watching. This matters for interpreting the Kittitas County event because it reframes what the record is actually telling us. When meteorologists say the May 2nd landspout was the first tornado ever recorded in Kittitas County, the emphasis should be on the word recorded. It is not a statement about the atmosphere's previous behavior over those mountains. It is a statement about the limits of human observation. The mountains almost certainly hosted occasional vortices over the decades and centuries before anyone was documenting them, spinning briefly over ridges and vanishing into the trees without leaving any mark in any database. What changed on May 2nd was not the atmosphere. What changed was the probability that a witness with a camera would be in the right place at the right moment. And that probability has been changing steadily for years, driven by the same forces that have transformed weather observation everywhere. The smartphone revolution is the obvious driver, but it is not the only one. The growth of outdoor recreation in mountain regions has put more people in remote terrain than at any point in history. Hiking trail cameras, wildlife monitoring networks, and amateur naturalist photography have extended visual coverage into places that used to be essentially unobserved. Climate enthusiasts and amateur meteorologists, equipped with social media and the ability to quickly share and identify what they are seeing, have created a distributed reporting network with a reach that no professional meteorological service could have built on its own. The result is a record that is growing not just forward in time, as new events occur and are documented, but also outward in space, as regions that were previously underobserved begin to appear in the data with more frequency. We are not necessarily seeing more tornadoes in the Mountain West. We are almost certainly seeing more of the tornadoes that were always there. This is a subtle but important distinction, and it means that any attempt to draw conclusions about trends in tornado frequency from the current data has to account for the changing efficiency of the observation network itself. The specific terrain of the Eastern Cascades, where the Wenatchee Mountains sit, adds another layer of complexity to this picture. These mountains are not just topographically complex, they are atmospherically complex in ways that have been studied for decades but are still not completely understood. The interaction between the Cascade Barrier and the prevailing westerly flow of the atmosphere creates a zone of highly variable weather on the eastern slopes. Air that has been wrung dry by the Cascades descends rapidly toward the Columbia Plateau, creating the warm and dry conditions that make eastern Washington so different from the wet maritime climate of the western lowlands. But this descent, called foehn flow or in the local vernacular the Cascades rain shadow effect, does not happen uniformly or predictably. When the large-scale pattern disrupts the normal east-west flow, when a trough of low pressure approaches from the north or a blocking ridge builds to the east, the atmospheric dynamics over the eastern slopes can become genuinely wild. Temperature inversions develop and collapse. Wind shear, the change in wind speed and direction with altitude, can become extreme over short distances because of the way the terrain channels and deflects flow. Thunderstorms that might be unremarkable over flat terrain become much more complex when they encounter the mountain boundary layer. All of this creates an environment where the basic ingredients for vortex formation, rotation near the surface, a rising column of air above it, and sufficient instability to maintain the connection between the two, can come together in ways that would not be possible over simpler terrain. The people who study atmospheric dynamics and complex terrain spend a lot of time thinking about a phenomenon called horizontal wind shear and what happens to it when convection develops. Under the right conditions, a zone of horizontal wind shear, think of it as a seam in the atmosphere where air moving in one direction meets air moving in a different direction, can be stretched and tilted by a developing convective cloud into a vertical vortex. This is, at its core, what happens in a landspout, and it is the process that the May 2nd event likely exemplified. The specific terrain of the Wenatchee mountain ridges and valleys probably contributed to the development of the horizontal shear zone that eventually got pulled upward into the landspout. If that reconstruction is correct, it has interesting implications. It suggests that the same terrain features that have always existed in Kittitas County, the same ridges and valleys and channeling effects, have always had the potential to contribute to vortex formation under the right atmospheric conditions. The landspout was not a fluke in the sense of being caused by something unusual about the terrain. The terrain was doing what it always does. What was unusual was the atmospheric setup that arrived on May 2nd and interacted with that terrain in a way it probably had not interacted in the documented record. This kind of thinking, about recurring potential rather than single event flukes, is central to how operational meteorologists approach the question of local severe weather climatology. Every county in the United States has some suite of atmospheric ingredients that its terrain and climate allow for, and some set of those ingredients that it essentially never sees. The challenge for a forecaster is knowing which is which, and not allowing the sparseness of the historical record in remote areas to lead to overconfident conclusions about what is and is not possible. The lesson of Kittitas County is a lesson about that overconfidence. The historical record said tornado risk was 0. The atmosphere said otherwise. There is a name for this kind of conceptual trap, this tendency to confuse the absence of observed events with the absence of possible events. In risk analysis, it is sometimes called the Lucretius problem, after the Roman poet who wrote that a wise man imagines the ship of state as the largest ship he's ever seen. The largest ship he has ever seen is the limit of his imagination, and so he never considers the possibility of a ship larger than that. Applied to weather, the Lucretius problem shows up when forecasters and planners assume that the most extreme event in the historical record defines the upper limit of what the atmosphere is capable of. It does not. The record is always finite. The atmosphere is not. In emergency management and infrastructure planning, the consequences of the Lucretius problem can be severe. Flood control systems designed to handle the 100-year flood of record may be inadequate if the true 100-year flood is actually larger. Tornado shelters and building codes developed based on local tornado history may be inadequate if the local history is too short or too incomplete to capture the full range of possible events. The expansion of the record by events like the May 2nd landspout is therefore not just scientifically interesting. It is practically important. It changes the risk calculus for the region in ways that have real implications for how people plan and prepare. Not that a single weak landspout in the Wenatchee Mountains is going to trigger a wholesale revision of building codes in Kittitas County. That would be a disproportionate response to a single event. but it adds a data point to a set of data points that collectively suggest the atmospheric capabilities of the Pacific Northwest are broader than a naive reading of the short historical record would indicate, combined with other unusual atmospheric events that have occurred in the region over recent decades, events that pushed against the expected boundaries in various ways. The picture that emerges is of an atmosphere that is more diverse in its behaviours than we sometimes give it credit for. The Pacific Northwest has a specific atmospheric personality in the popular imagination, defined by persistent low clouds, drizzle, occasional dramatic windstorms, and the kind of weather that makes people move to Seattle and then spend years slightly confused about whether they are happy with that decision. That personality is real and rooted in genuinely characteristic atmospheric patterns driven by the Pacific Ocean and the Cascade Barrier. But it is not the whole story. The atmosphere over this region is capable of producing events that fall well outside the personality profile, and those events, when they occur, tend to surprise people precisely because they conflict with the established mental model. Severe thunderstorms in western Washington are a good example. The region gets them occasionally, much less frequently than the Central Plains or the Gulf Coast, but with enough regularity that experienced Pacific Northwest residents have seen their share of dramatic lightning and heavy rain. What surprises newcomers and even some long-term residents is the intensity that some of these events can achieve. Western Washington thunderstorms are not supercells. They are not the multi-hour, multi-county spanning events that define severe weather in Tornado Alley, but they can produce significant lightning, large hail, and damaging winds, and when they occur they tend to catch people off guard precisely because the regional weather personality says this kind of thing does not really happen here. In the meteorological community, there is an ongoing effort to resist that kind of regional stereotyping. The goal is to understand not what a place's atmosphere usually does, which is well established by the existing record, but what it is capable of doing across the full range of possible conditions. This is sometimes called the probabilistic hazard assessment approach, and it requires looking beyond the historical record to the underlying physics of what the terrain and atmosphere could, in theory, produce. Modelling studies, climatological analyses, and case studies of unusual events all contribute to this kind of assessment. The May 2nd landspout will eventually become part of that literature for Kittitas County and the surrounding region. There is a separate and fascinating dimension to the story of this particular event, which is the question of what it was like to be the person who witnessed and recorded it. We do not know everything about the specific circumstances of the observation, but we know enough to reconstruct the general situation, and what it tells us is something interesting about the phenomenology of witnessing extreme weather in a place where it is not expected. When someone encounters a tornado, even a weak one, the first cognitive response is often disbelief. The visual signal conflicts with the mental model. You're in a place that does not have tornadoes, and yet the shape descending from the cloud base is unmistakable. There's a brief period where the brain tries to rationalize what the eyes are seeing, to find an explanation that does not require accepting the presence of something that should not be there. A dust devil, maybe, or a waterfall seen from an unusual angle, or some trick of the light. And then the rational mind gives up trying to explain it away, and you're left with the simple, disorienting experience of watching something unprecedented. People who have witnessed first-instance extreme weather events in unexpected locations consistently describe this quality of cognitive dislocation. The event is real. The evidence is right there, and yet some part of the mind keeps trying to reconcile what is being seen with what is supposed to be possible in this place. The reconciliation, when it finally happens, carries an almost physical weight. The world you thought you understood turns out to be larger and stranger than you realized, and the specific landscape you are standing in turns out to hold possibilities you never imagined. For the observer on May 2nd, the footage they captured will have a permanence that extends far beyond the event itself. It is not just a personal memory or a local curiosity. It is a scientific record. It will be studied. It will be cited. It will be referenced in future discussions of tornado occurrence in complex terrain and the climatology of the Eastern Cascades. In a real sense, the moment when that person decided to raise their phone and start recording was the moment when this event entered the permanent conversation of atmospheric science. The tornado existed regardless of whether it was filmed, but its existence in the scientific record depends entirely on that decision. This is one of the ways that the relationship between science and the general public has changed most profoundly in the era of widespread digital documentation. Professional meteorologists and trained storm spotters used to be the primary conduit through which unusual atmospheric events entered the scientific record. That conduit still exists and remains important, but it is now supplemented by a vast and distributed network of ordinary people who happen to be in the right place at the right time with a device capable of capturing what they see. The scientific value of that network is hard to overstate, and events like the Kittitas County landspout are among its most tangible products. The way the footage travelled, from initial capture to social media to local news to weather service analysis, follows a path that would have been impossible to predict even 20 years ago. Speed matters enormously here. The time between capture and official verification, which in previous eras might have taken weeks, compressed to days or even hours as the footage circulated and reached people with the expertise to assess it. This compression has practical value for warning systems, but it also has scientific value. The atmospheric data associated with the event, the radar signatures, the surface observations, the upper air soundings are most complete and most useful in the hours and days immediately following the event. The sooner the footage reaches analysts, the better the reconstruction they can produce. One thing the reconstruction will almost certainly focus on is the visual characteristics of the landspout itself, because landspouts leave optical signatures that carry information about their internal dynamics. The width of the funnel at cloud base versus the width at ground level tells you something about the depth of the layer in which rotation is occurring. The degree to which the funnel tilts from vertical tells you something about the wind shear environment in which it formed. The opacity or translucency of the funnel tells you something about the humidity of the air being pulled into the vortex and whether condensation is occurring all the way to the ground or only part way down. All of this is embedded in the footage, waiting to be extracted by people who know what to look for. The funnel in the Wenatchee Mountains footage appears, by early accounts, to have been relatively narrow and relatively vertical, which is consistent with a landspout forming in an environment of modest wind shear. A highly tilted funnel would suggest stronger shear, which in turn would affect the structural dynamics of the vortex itself. The narrowness is also consistent with a landspout rather than a tornado of mesocyclonic origin, because the fundamental rotation source in a landspout is a relatively shallow surface layer rather than the large-scale deep rotation of a supercell. The visual appearance of the vortex is, in other words, physically coherent with the meteorological interpretation of how it formed. The footage and the analysis tell the same story. This kind of physical coherence between visual appearance and meteorological mechanism is not always present in tornado footage. Wind devils and dust whirls, which are visually tornado-like but are driven by completely different physical processes involving strong surface heating rather than organized convection, can fool observers and even briefly fool automated detection systems. The difference in context, a clear sky and strong sunshine for a dust devil versus a developing convective cloud for a landspout, is usually diagnostic. But in complex terrain where cloud shadows can create locally cold and locally warm surface patches, and where terrain-driven surface flows can produce localized swirling, the boundary between a genuine vortex and a non-meteorological visual effect can occasionally be ambiguous. The verification process exists partly to navigate exactly these ambiguities. In the case of the May 2nd event, the verification apparently did not take long to complete. The combination of clear visual evidence, consistent atmospheric context, and the absence of any plausible alternative explanation for what was seen moved the analysis quickly toward confirmation. The meteorologists who reviewed the case were, by all accounts, quite confident in their conclusion. What they were less certain about, and what remains genuinely uncertain, is the precise chain of atmospheric events that set up the conditions for the vortex to form in that specific location on that specific afternoon. The reconstruction of the setup involves going backward through the data, trying to identify the precursor conditions that made the Eastern Cascades unusually favourable for convective development on that day. Surface temperature data, wind observations, and upper air soundings all contribute to this picture, but the spatial resolution of the observing network in this region is not high enough to capture the fine-scale surface flow patterns that probably played a central role in the development of the horizontal wind shear that preceded the tornado. The mountains essentially filter the atmospheric signal through a terrain so complex that the standard observing network cannot fully resolve what is happening near the surface. This is a problem that researchers working on mountain meteorology have been wrestling with for decades, and it has prompted the development of specialized observing strategies for complex terrain, including dense networks of surface stations, instrumented towers on ridges, and increasingly the use of small unmanned aircraft that can fly into areas and at altitudes inaccessible to standard observing platforms. None of these approaches can be deployed everywhere, and the Wenatchee Mountains are not a place with an unusually dense observing network, but the post-event analysis of the May 2nd case may prompt some thought about whether targeted observations in this region could improve the understanding of its convective potential. The broader conversation about convection in complex terrain is one of the most active areas of modern mesoscale meteorology. Mesoscale refers to the middle range of atmospheric phenomena, the scale between the large global circulation patterns that govern climate and the microscale turbulence of individual gusts and eddies. Thunderstorms, tornadoes, and landspouts all fall within the mesoscale, and the study of how terrain at this scale interacts with atmospheric instability to produce or suppress convective phenomena is genuinely difficult. The interactions are nonlinear, meaning that small changes in the initial conditions can produce large and sometimes counterintuitive changes in the outcome. This is part of why tornadoes, even in regions where they are expected, remain challenging to forecast with high precision. In regions where they are unexpected, the challenge is compounded by the fact that the atmospheric setup may look quite different from the canonical precursor patterns that forecasters learn to recognize. On May 2nd, the forecasters responsible for the Kittitas County region presumably saw a relatively benign convective setup, perhaps some afternoon thunderstorm potential, driven by surface heating and modest instability, but nothing that would have flagged in their severe weather assessment criteria as a landspout risk. This is not a criticism of the forecasters. Predicting landspout formation in complex mountain terrain is not currently within the practical capabilities of operational meteorology. The atmospheric models that forecasters use do not resolve the fine-scale surface flow features that are critical to landspout development, and the observational data needed to identify the precursor surface shear zone in real time does not exist for remote mountain areas. The event was, from an operational forecasting perspective, essentially unpredictable given the available tools. This unpredictability is worth sitting with, because it highlights a gap between scientific understanding and operational capability that exists across a range of atmospheric phenomena. We understand, in general terms, the physical mechanisms that produce landspouts. We understand that complex terrain can create the surface flow features that feed into those mechanisms, but translating that general understanding into specific, location-specific, hour-by-hour forecasts is a different challenge entirely, and one that current technology and observing networks are not yet equipped to meet. The May 2nd event sits in that gap, understandable in retrospect, essentially unforeseeable in real time. Whether that gap will narrow in the coming years depends partly on advances in numerical weather prediction, particularly the development of high-resolution models capable of representing the fine-scale atmospheric structures that form near complex terrain. It depends partly on advances in the observing network, particularly in remote areas where the current coverage is thin, and it depends partly on advances in machine learning and pattern recognition, which offer the possibility of identifying precursor signals in complex data sets that human analysts might overlook. All of these developments are actively in progress, and the overall trajectory of operational weather forecasting is toward higher resolution, greater coverage, and better predictive skill at shorter time ranges. But there will always be events that push against the limits of predictability, events driven by scale interactions so fine or by initial conditions so precisely balanced that no practical observing network can capture them completely. Landspouts in mountain terrain are likely to remain in this category for the foreseeable future. They are too small, too brief, and too dependent on fine-scale surface features to be reliably forecast by any system currently available or likely to be available in the near term. The most we can do is understand the general conditions that favour them, warn people when those conditions are broadly present, and continue to document them when they occur so that the scientific understanding of their formation gradually improves. The documentation itself is therefore not a passive activity. It is an active scientific contribution. Every verified tornado in the historical record represents a constraint on the models of atmospheric behaviour, a data point that any adequate theory of tornado formation has to be able to explain. Single events carry particular scientific weight when they push against the existing models, when they occur in places or under conditions that the prevailing understanding would suggest are unfavourable. The Kittitas County landspout is exactly this kind of event, and the detailed reconstruction that meteorologists will eventually produce from it will contribute to refining the models of landspout formation in ways that have value well beyond this one county. There is another dimension to the story of tornadoes in unexpected places that we have not yet touched on, and it is one that takes the discussion in a direction that might seem surprising at first. It involves not the Pacific Northwest, but a location even less associated in the popular imagination with tornado activity, the British Isles. The United Kingdom has tornadoes. This is not widely known outside the meteorological community, and it surprises almost everyone who hears it for the first time. When people think of tornadoes, they think of the American Midwest, not the English countryside. The image of a funnel cloud over a field of wheat in Worcestershire simply does not fit the mental template. And yet tornadoes occur in the United Kingdom with a regularity that makes the UK one of the highest density tornado environments in the world, measured by number of events per unit of land area. The numbers are genuinely striking. Estimates of annual tornado frequency in the UK range from roughly 30 to over 100 events per year, with some studies suggesting the true figure may be higher when accounting for unobserved events. These are almost all weak tornadoes, rarely reaching what would be classified as significant intensity on the standard measurement scale. They are short-lived, typically travelling less than a mile and lasting a few minutes at most. They are diffuse enough that they cause relatively little damage compared to their American counterparts. But they are real. They meet the meteorological definition. They are tornadoes. Why does this happen? The answer lies in the specific atmospheric dynamics of the Atlantic margin of Europe, and the way the British Isles are positioned relative to them. The UK sits at the end of the Atlantic storm track, the corridor along which low-pressure systems generated over the ocean travel eastward toward Europe. These storms bring strong wind shear, the sharp changes in wind speed and direction with altitude that are one of the key ingredients for vortex formation. The maritime surface, even over land areas that are only a short distance from the ocean, provides enough moisture and instability during the transition seasons to generate convective showers, and the relatively modest terrain of England and Wales, less dramatic than the Cascades but still capable of generating localized surface flow variations, provides the final ingredient. The result is that the atmospheric conditions required for weak tornado formation occur relatively frequently over England and Wales, particularly in autumn and spring when the contrast between the still warm ocean and the cooling continental air mass is greatest. The tornadoes that result are nothing like the monsters of the American Great Plains, but they are genuine tornadoes, and their frequency is a useful reminder that tornado formation is a fundamentally atmospheric process that does not require any specific kind of landscape or climate. The British tornado climatology was not well documented until relatively recently. A network called the Tornado and Storm Research Organisation, made up largely of amateur meteorological enthusiasts, has spent decades systematically collecting, verifying and cataloguing tornado reports from across the UK. Their database is one of the most comprehensive in the world for any non-American region, and it has fundamentally changed what scientists know about tornado frequency in the Atlantic maritime environment. Before the network existed, the conventional wisdom was that UK tornadoes were interesting anomalies, rare enough to be treated as individual curiosities. The systematic collection of data revealed instead a regular and predictable phenomenon with its own seasonal patterns, geographic distribution, and meteorological signatures. This is essentially the same transformation that has happened in the Pacific Northwest, just on a larger scale and over a longer time period. In both cases, the prior perception of tornado rarity was partly a product of incomplete observation rather than genuine meteorological scarcity. In both cases, systematic effort to collect and verify reports revealed a phenomenon that was more common than the previous record suggested, and in both cases, the revelation required both technological tools, cameras in the UK case, smartphones and social media in the Pacific Northwest case, and organised effort to compile and analyse the resulting data. The lesson is consistent. Atmospheric phenomena are not distributed in the ways that sparse historical records suggest. The record reflects what was observed, and what was observed reflects where people were and what tools they had. Expand the observation network and you expand the apparent range and frequency of the phenomena. This does not mean that the Wenatchee Mountains are about to develop a tornado season. It means that the baseline frequency of unusual events there is probably somewhat higher than the record, as it existed before May 2nd, would indicate. There is a place in England that has the highest tornado density of any comparable area in the British Isles, and it lies in a flat agricultural zone east of the Pennine Hills, where the atmosphere sometimes seems to conspire to produce brief rotating vortices with unusual regularity. Locals have noticed this pattern. There is a name for it. The unofficial tornado corridor of England runs roughly through the English Midlands and East Anglia, and while the tornadoes there are weak enough that they rarely make national headlines, they occur often enough that people in the area have developed a kind of matter-of-fact familiarity with them that mirrors the relationship residents of Oklahoma have with their own, much more violent atmospheric neighbours. This familiarity is meteorologically significant. It means people notice and report events that elsewhere might go unrecorded, because the regional culture has developed a framework for understanding them. The tornado that touches down briefly in a farmer's field in Lincolnshire and knocks over a fence gets reported not because the farmer thinks it is unusual, but because the farmer knows what it is, and knows that people who track such things want to know about it. That cultural knowledge, transmitted by the tradition of amateur weather observation that has deep roots in British culture, is part of what makes the UK database as complete as it is. Contrast this with the situation in the Wenatchee Mountains. There is no tradition of tornado watching in this region. There is no local cultural framework for understanding or reporting such events. A landspout spinning over a remote ridge is not something that the regional weather vocabulary readily accommodates. The observer who captured the May 2nd footage was probably operating without any prior expectation that what they were seeing would be scientifically significant, let alone historically unprecedented for their county. The cultural infrastructure for translating this kind of observation into a verified scientific record had to be improvised in real time through social media sharing and the availability of official channels for submitting unusual weather reports. This improvised quality is actually quite common for first-instance extreme weather events in regions with limited severe weather history. The person who witnesses something unprecedented in their local atmosphere is working without a script. They have to figure out on their own that what they are seeing is real, worth recording, worth reporting, and worth following up on. The fact that the May 2nd observation made it through all of those steps and ended up in the official record is a product of individual initiative operating in an environment that, while not culturally prepared for tornado documentation, had the technological infrastructure to support it. The question of who actually observed the event and under what circumstances is not something the public record has fully resolved, and that is appropriate. Weather reporting does not require and does not expect that the individuals who submit observations become public figures. What matters scientifically is the quality of the data, not the biography of the person who captured it. But the circumstances of the observation are part of the larger story about how the record gets built, and they are worth thinking about even if the specific details remain private. The most likely scenario, given the terrain and the time of year, is that the observer was engaged in some form of outdoor recreation in the Wenatchee Mountains area on a May afternoon, the kind of activity, hiking, trail running, mountain biking, that draws people into this terrain regularly in the spring. The combination of convective cloud development and the mountain setting would have created a visually dramatic sky even before the landspout formed, the kind of sky that invites photography. When the vortex appeared, it was probably already being photographed, which is why the footage exists and appears to be of good quality rather than a hasty and blurry reaction shot. This kind of serendipitous alignment between outdoor recreation and weather observation has produced some of the most scientifically valuable tornado footage in history. Tornadoes photographed from mountain roads during camping trips, waterspouts caught by kayakers, brief landspouts filmed by trail runners on exposed ridges. The scientific value of these observations is not diminished by the fact that they were collected by accident rather than by design. In many cases, they are more valuable than footage collected by deliberate storm chasers because they capture events in locations and under conditions that chasers would not normally target. The growth of outdoor recreation in the American West over the past 3 decades has been dramatic. National park visitation has reached record levels. Trail systems that were previously lightly used have become thoroughfares during peak seasons. Remote mountain areas that once saw only occasional hikers now see steady traffic on summer weekends. This demographic shift has had measurable effects on the observational coverage of remote terrain, including weather phenomena. The The frequency with which unusual atmospheric events are captured in mountain regions has increased in rough proportion to the increase in human presence in those regions, and the trend shows no sign of reversing. From a purely meteorological standpoint, this is welcome. The Mountain West is large, remote, and atmospherically complex enough that increasing observational coverage there will continue to yield genuine scientific surprises for years to come. Events that push against the historical record, firsts and extremes and outliers, will continue to appear as the network of potential observers extends deeper into terrain that was previously largely invisible to the formal observational system. The Kittitas County landspout is an early product of this trend, but it will not be the last. What else might the Eastern Cascades be hiding? The question is not rhetorical. There are specific atmospheric phenomena that the current record almost certainly underrepresents in this region, and landspouts are actually not the most striking of them. The interaction between the Cascade Barrier and the broader atmospheric circulation can, under certain conditions, generate mesoscale convective systems, organized clusters of thunderstorms that are much larger and more persistent than the ordinary afternoon convection driven by surface heating. These systems are well documented over the Plain States, where they are known to produce significant severe weather including tornadoes. They have been observed occasionally over the Pacific Northwest, but the frequency with which they affect the Eastern Cascades and the specific ways in which the terrain modifies their behavior is not well characterized. Similarly, the region occasionally experiences what forecasters call elevated convection, thunderstorms that develop not from surface heating, but from processes operating in the middle and upper atmosphere, where there is insufficient moisture or instability. Elevated convection can produce lightning and hail, and occasionally significant wind gusts, but because it is not anchored to the surface, it behaves quite differently from ordinary surface-based thunderstorms. Its occurrence in the Eastern Cascades is another area where the current record probably underrepresents what the atmosphere actually does, and where more complete documentation would produce a more accurate and more useful picture of the regional severe weather climatology. The challenge in both of these cases, and in many others like them, is the same challenge that made the Kittitas County landspout surprising. The existing record, built over decades of surface-based observation in a relatively sparse network, does not have the resolution or coverage to capture all of the atmospheric behaviors that occur in complex terrain. The gap between what the record shows and what the atmosphere actually does is real and substantial. Closing that gap requires not just more technology and more observers, but a cultural shift in how people in the Pacific Northwest think about their relationship to extreme weather. That cultural shift is already beginning to happen, driven partly by events like the May 2nd landspout, and partly by the broader national conversation about extreme weather and its relationship to a changing climate. People in the Pacific Northwest who might once have thought of dramatic atmospheric events as something that happened to people in other parts of the country are increasingly aware that their own region has atmospheric capabilities that were previously underappreciated. The heat dome that affected the Pacific Northwest in June of a year not far back, producing temperatures that exceeded anything in the region's recorded history by wide margins, was a particularly powerful accelerant of this cultural shift. If that event could happen here, the thinking goes, then perhaps the atmosphere over this region is more capable of extremes than anyone realized. That reasoning is not wrong, but it requires some careful unpacking. The heat dome and the Kittitas County landspout are very different kinds of events driven by very different atmospheric mechanisms. The heat dome was a product of a large-scale circulation anomaly, a persistent blocking pattern that trapped hot air over the region for an extended period. It was unusual not because the Pacific Northwest lacks the ability to produce heat, but because the particular configuration of the large-scale atmospheric circulation that produced it was extraordinarily rare. The landspout, on the other hand, was a small-scale local event driven by the interaction of convective cloud development with terrain-induced surface flow features. These are different physical stories, and conflating them can lead to confused thinking about the nature of atmospheric extremes in this region. What they share is that both pushed against the prior expectations encoded in the historical record. Both were unprecedented in some sense, and both, when they occurred, prompted a reassessment of what the local atmosphere is capable of. That reassessment is valuable regardless of what is driving the events, and the accumulation of events that require it is one of the ways that scientific understanding of regional climatology gradually matures. The The scientific maturation of regional severe weather climatology is not a glamorous process. It does not happen through dramatic single discoveries. It happens through the slow accumulation of case studies, through the patient building of databases, through the incremental improvement of models and observing networks, through the quiet revision of prior conclusions in the light of new evidence. The May 2nd landspout will contribute to this process in ways that are real, but mostly invisible to anyone outside the meteorological community. The paper that will eventually be written about the event will appear in a journal that relatively few people read. It will be reviewed by specialists in mesoscale meteorology and complex terrain dynamics. It will add to the literature in ways that are meaningful to people working on tornado climatology in the western United States, and that will be cited by future papers working on related questions. It will not make the news again, or if it does, only briefly. And then it will exist quietly in the scientific literature, part of the permanent record of atmospheric events, available to anyone who wants to understand what happened in the Wenatchee Mountains on the 2nd of May. This is how science mostly works, not through grand revelations, but through small, careful additions to the store of verified knowledge. The landspout will join thousands of other carefully documented atmospheric events in the growing scientific literature on complex terrain meteorology, each one contributing a little more to the overall picture of what the atmosphere can do in places where the terrain makes its behavior especially difficult to predict. There is a quality to the event that goes beyond its scientific significance, though, and that quality has to do with what it means to live in a place and to discover that the place holds surprises you never expected. This is not unique to meteorology. Geology reveals surprises too, faults that were not on any map until they moved, ancient volcanic deposits that change the reconstruction of a landscape's entire history. Biology does the same, new species turning up in habitats that have been studied for decades, behaviors documented for the first time in animals whose lives were thought to be well understood. The world keeps revealing that it is larger and more complex than our knowledge of it, and there is something both humbling and exciting about that. For the people who live in the Wenatchee Valley, the mountains above them just demonstrated that they can do something no one had ever seen them do before. That knowledge changes the relationship between the residents and the landscape in a small but real way. The mountains are still the same mountains they have always been. The weather that flows over them still operates according to the same physical laws it always has. But the range of behaviors those laws can produce in that specific terrain has just expanded, in the human record if not in physical reality, and that expansion matters for how people understand the place where they live. There is a tradition in human cultures of paying close attention to the weather of a specific place, of developing detailed local knowledge about what the sky means and what is coming. This tradition was practically essential for farming communities and fishing communities throughout history, and it produced bodies of knowledge that were in many ways sophisticated, even if they were expressed in terms of proverbs and sayings rather than equations and models. The saying "red sky at night, sailor's delight, red sky in morning, sailor's warning" is not scientific in the formal sense, but it encodes a genuine atmospheric truth about the relationship between the colour of evening and morning skies and the likelihood of approaching precipitation. Local weather wisdom is full of these encoded observations, built up over generations of careful attention to how the atmosphere behaves in a specific place. The Wenatchee Valley has its own version of this local knowledge, developed by the farming communities and outdoors enthusiasts and long-time residents who have spent decades reading the sky above the mountains. But no part of that accumulated knowledge included the possibility of a tornado. The local atmospheric vocabulary did not have that entry. And now, for the first time, it does, not as an abstract possibility noted in a textbook, but as a concrete, documented, filmed reality that happened on a specific afternoon in a specific year. The local knowledge has been updated. Updating local knowledge is not always a comfortable process. There can be resistance to information that conflicts with deeply held assumptions about a place and its capabilities. Some of the most significant meteorological disasters in history have been exacerbated by the failure of local knowledge to incorporate new information about what a familiar landscape could do. Communities that had never experienced a major flood, and whose local wisdom said the river did not flood like that, found themselves unprepared when the river did exactly that. Communities that had never experienced a major earthquake, because the fault was not in any catalogue, and the local geology did not look to untrained eyes like earthquake country, found themselves building on ground that was perfectly capable of violent motion. The Kittitas County landspout is not the precursor to a disaster. A weak, brief, remote area vortex is not the kind of thing that demands a rethinking of disaster preparedness. But the pattern it exemplifies, the pattern of the local record failing to capture the full range of what the local atmosphere can do, is exactly the pattern that does matter for preparedness in other contexts. The atmospheric record of any specific region is, to some degree, a function of how long and how carefully that region has been observed, and the shorter and less careful the observation history, the more likely it is that the record underestimates the true range of possible events. For emergency managers and planners in the Pacific Northwest, this is relevant not just for tornadoes, where the practical risk is genuinely low, but for a range of atmospheric phenomena where the risk is higher. Flash flooding, debris flows triggered by intense convective rainfall, severe thunderstorm wind damage, large hail, these are all phenomena that occur in the region with some regularity, and that are governed by the same basic question of what the local atmosphere is capable of. The more complete and accurate the understanding of that capability, the better prepared people can be. The National Weather Service forecast offices in the Pacific Northwest have been working for years to improve their understanding of the regional severe weather climatology, and the May 2nd event gives them one more data point to work with. It also gives them a case study in how complex terrain can produce atmospheric behaviours that standard forecasting approaches are poorly equipped to anticipate. The analysis of this event will likely feed back into the thinking about how to communicate severe weather risk in complex terrain areas, how to calibrate the thresholds used for issuing severe weather statements, and how to think about the places where the current forecasting tools are most likely to be surprised. This kind of operational learning from outlier events is one of the most valuable outputs of the weather observation and verification system. When something happens that was not predicted and not expected, the question is not just what happened, but what it reveals about the limitations of the predictive system. The Kittitas County landspout reveals something specific, namely that the surface flow features that can trigger landspout formation in complex terrain are not currently detectable by the observing network in real time, and that the atmospheric models used for operational forecasting do not resolve them with sufficient fidelity to produce reliable forecasts of this type of event. Knowing what you cannot predict is actually a crucial piece of information for operational meteorology. It tells forecasters where to be appropriately humble in their public communications. It tells them which kinds of severe weather to flag as possible, even when the specific hazard assessment tools do not show a strong signal. And it tells the research community where the most valuable improvements to the forecasting system could be made. The gap between what happened on May 2nd and what the forecasting tools could have predicted in advance is, in effect, a research agenda item, a specific problem that better observing systems or better models might eventually be able to address. Whether it is worth the investment to specifically target complex terrain, landspout forecasting, with improved tools, is a cost-benefit question that depends on how frequent such events are and how much damage they cause. A single weak landspout in a remote mountain area is not in itself a strong argument for major investment. But the broader class of small-scale convective vortices in complex terrain includes phenomena more dangerous than the May 2nd event, including gustnadoes associated with outflow boundaries from thunderstorms, brief spin-ups near terrain features during windstorm events, and occasional stronger tornadoes that develop in the transition zone between the Cascades and the interior plateau. The cumulative case for better understanding of vortex formation in this environment is more substantial than any single event suggests. The research that grows out of the May 2nd case will likely connect to a broader body of work on tornado occurrence in the western United States that has been slowly developing over the past 2 decades. The perception that tornadoes are essentially absent from the Mountain West is not accurate, and researchers have been assembling evidence to that effect for some time. There are documented tornado events in western Colorado, in the foothills of northern California, in the highlands of Arizona and New Mexico. Each of these represents a challenge to the conventional wisdom about where tornadoes occur and why. Collectively, they paint a picture of an atmospheric capability that extends far beyond the boundaries of the traditional tornado belts. What these western tornadoes share with each other, and with the Kittitas County event, is that they tend to be weak, short-lived, and often associated with non-supercell convection. They are products of the fine-scale atmospheric dynamics of complex terrain, rather than the large-scale organized convection that drives the most violent tornado outbreaks. They are real, but they are not, in most cases, operationally dangerous, in the same way that a violent supercell tornado is dangerous. This distinction is important for putting them in their proper context. The first tornado in Kittitas County is scientifically interesting and historically significant. It is not the beginning of a Great Plains-style tornado problem for the Wenatchee Valley, but the distinction between scientifically interesting and practically threatening should not lead to dismissiveness. The atmosphere does not always produce events in the categories that prior experience suggests. One of the recurring lessons of meteorological history is that the specific nature of an extreme event often differs from what was expected, even when the general possibility was known. A region that has never experienced a violent tornado but has experienced weak ones now knows that some level of tornado production is within the atmospheric repertoire of its terrain. That is useful information even if the probability of a violent tornado there remains extremely low. The historical record in the Mountain West is now slowly being built, event by event, case study by case study, into something more complete and more accurate than the record that existed a generation ago. The contribution of events like the May 2nd landspout to that record is cumulative and real, even if any single event is just one data point. The picture that emerges from this growing record is of a mountain atmosphere that is more varied, more capable of extreme behavior, and more poorly understood than the previous sparse record suggested. That is not a cause for alarm, it is a cause for continuing attention, for continued investment in the observation and analysis that builds scientific understanding, and for the kind of epistemic humility that recognizes the difference between what we have observed and what is actually possible. Epistemic humility is not a virtue that comes naturally to any field of human endeavor, and meteorology is no exception. The forecasting enterprise depends on confidence, on the ability to make public statements about what the atmosphere will do based on incomplete information, and to do so in ways that are useful to the people who depend on forecasts to make decisions. That confidence is necessary and appropriate for operational purposes, but it needs to be balanced by an equally appropriate awareness of the limits of the knowledge on which the confidence is based, and by openness to revising prior conclusions when new evidence demands it. The May 2nd event is a small but genuine demand for such revision in the specific context of the Kittitas County severe weather climatology. The revision is small. The probability of a tornado there remains low. The baseline expectation for what a typical May afternoon sky over the Wenatchee Mountains will produce has not changed in any practical sense. But the theoretical possibility is no longer zero, and that shift from zero to something non-zero, however small, is the essential content of what the record revision means scientifically. There is something almost mathematical about the significance of that shift. In probability theory, there is a categorical difference between an event with probability 0 and an event with any positive probability at all, no matter how small. An event with 0 probability cannot occur. An event with even the tiniest positive probability can and eventually will occur if you wait long enough. The prior record, with its long string of zeros, implied that the probability of a Kittitas County tornado was 0. The May 2nd event proves that it is not. The actual probability is unknown, perhaps very small, perhaps somewhat larger than the sparseness of the record suggests, but it is definitely not 0. And that categorical shift, from impossible to possible, is the most fundamental thing the event establishes. All of this brings us back to a question that is easy to overlook when the focus is on meteorological mechanisms and historical records and operational forecasting, and it is the question of what we actually mean when we say we know a place. The residents of the Wenatchee Valley know their mountains. They know the way the afternoon light falls on the ridges in late spring. They know the wind patterns that come with different kinds of weather. They know when to expect snow to linger and when to expect it to be gone. They have, in the aggregate, an intimate familiarity with the atmospheric character of their home landscape, and yet on May 2nd, the mountains demonstrated something that no one in the living memory of that community had ever seen them demonstrate. This is not a failure of local knowledge. It is a reminder that local knowledge, no matter how deep and detailed, is always an incomplete encoding of the full range of what a landscape can do. The mountains hold possibilities that are realized too rarely to appear in any human memory, too rare even to appear in the 75 years of formal record-keeping that preceded the event. Those possibilities are real. They are written into the physics of the terrain and the atmosphere that moves over it. They simply have not been expressed before, at least not in any form that reached the record. This is true of landscapes generally. The geologist who studies a mountain range knows that the range has been shaped by processes that operated over millions of years, and that the evidence for those processes is encoded in the rocks, readable if you know how to read it. The botanist who surveys a forest knows that the forest is the product of centuries of succession, disturbance, recovery, and adaptation, and that the species present in it reflect a long history of which only fragments have been directly observed. The meteorologist who studies the atmosphere over a region knows that the atmospheric record is a thin slice of what the atmosphere has actually done over the entire history of human settlement and beyond, and that the full range of the atmosphere's capabilities extends beyond the edges of that thin slice. We know places through what they have shown us, and what they have shown us is always less than what they are. The mountains that have never produced a tornado are not mountains that cannot produce one. They are mountains that have not yet produced one in the presence of someone who could document and report it. The distinction is the difference between absence of evidence and evidence of absence, and it matters everywhere that human knowledge of the natural world depends on the incomplete and biased sample provided by recorded observation. The history of science is substantially a history of that distinction being worked out field by field and case by case. The geologist who proposed continental drift was told that the continents were stable because the record showed no evidence of them moving. The biologist who proposed that deep-sea environments harboured complex life was told that the depths were too cold and too dark for anything beyond microbial communities, because the samples that had been collected from them were limited to the most accessible parts of the seafloor. The astronomer who suggested that the universe contained far more matter than we could see was told that the observable record was the relevant record. In each case, the prior conclusion drawn from the incomplete record was revised by better evidence and more careful reasoning about what the absence of observed evidence actually implies. Weather and climate are subject to the same intellectual dynamic. The prior record of the Wenatchee Mountains told meteorologists that Kittitas County was not tornado country. The correct response to that record in retrospect was not the conclusion that Kittitas County could not produce a tornado. The correct response was the conclusion that Kittitas County had not produced a documented tornado in the period for which records existed, and that the physics of the atmosphere gave no strong reason to believe it never would. Those are different statements, and the difference between them is the difference between the false confidence of the Lucretius problem and the appropriate humility of a science that knows the limits of its own record. Getting to that appropriate humility is not a simple intellectual exercise. It requires active effort to think against the grain of what the record suggests, to ask not just what has happened, but what could happen, to reason from physical principles rather than historical precedent when those two things conflict. It is easier and more natural to trust the record than to question it. The record feels like knowledge, and questioning it can feel like willful ignorance. But the record is always, in some sense, an artifact of the observation process, and the observation process has limitations that the record itself cannot encode. The meteorological community has developed some tools for this kind of reasoning. Atmospheric physics provides first principles constraints on what the atmosphere can do, and when the historical record seems to prohibit something that first principles say is possible, that tension is a signal for investigation rather than for uncritical acceptance of the record's apparent conclusion. Paleoclimatology, which extends the climate record back tens of thousands of years using ice cores, tree rings, and sediment deposits, has revealed extreme events in the distant past that had no analogue in the instrumental record. Proxy climatology for extreme weather events, using similar methods to reconstruct storm tracks, flood frequencies, and drought patterns beyond the range of direct observation, has similarly revised prior conclusions about what was and was not within the range of past atmospheric behaviour. For regions like the Pacific Northwest, where the direct instrumental record is both short and sparse in coverage, these longer-term and broader coverage approaches to understanding atmospheric capabilities are particularly valuable. The paleoclimatic record for the Pacific Northwest is not as detailed as for some other regions, but it does contain evidence of past climate states quite different from the present, with implications for the kinds of extreme weather events that would have been possible under those conditions. As the instrumental record continues to accumulate, the emerging picture of what the current atmosphere can do will be set against this longer-term context, and the overall assessment of regional atmospheric capabilities will be more complete as a result. This broader perspective is one reason why the Kittitas County landspout, small as it is in the grand scheme of atmospheric events, is worth the extended attention we have given it here. It is not important because of what it is, a brief weak vortex in a remote mountain county. It is important because of what it represents, the ongoing process by which the limits of the atmospheric record get pushed outward by the addition of genuine new observations in genuine new contexts. That process is fundamental to how science works and how scientific knowledge matures, and it is happening all the time, in hundreds of contexts simultaneously, in ways that collectively build toward a more accurate and more complete understanding of the natural world. The atmosphere that produced the May 2nd landspout has been doing what it did long before anyone was watching, and will continue to do it long after the specific event is forgotten by everyone except the specialists who cite the eventual paper. The ridges and valleys of the Wenatchee Mountains will continue to channel flow and create surface wind features and interact with developing convective clouds in the same ways they always have. On some future afternoon, under some future atmospheric setup, the ingredients will align again. Maybe next year, maybe in 30 years, maybe not for another century. The record does not know, and neither does any current model. What the record now knows is that the possibility is real. That is the gift of the May 2nd event. A modest gift in meteorological terms, but a genuine one. The possibility was always real, but now it is documented, part of the formal scientific record, available to anyone who wants to know what the atmosphere over Kittitas County can do. The mountains revealed something, and this time there was someone there to receive the revelation and pass it on. The work of weather science is, at some level, always this. It is the work of receiving what the atmosphere chooses to show, translating it into language that persists beyond the moment, and adding it to the accumulation of knowledge about what this restless and complex and endlessly surprising system is capable of. The people who do that work, the operational forecasters running models in the pre-dawn hours, the researchers analysing case studies in university offices, the amateur observers documenting unusual events on hiking trails, are all part of the same enterprise. They're all watching, recording, and reasoning about an atmosphere that never quite stops surprising them. The atmosphere over the Wenatchee Mountains is no different from the atmosphere anywhere else in this respect. It operates according to the same physics, responds to the same large-scale forcing, and expresses in its local behaviour the same fundamental principles that govern the global circulation. What makes it unique is what makes every specific place unique, the particular way those universal principles play out in the context of this specific terrain, this specific climate, this specific history of observation and documentation. The Kittitas County landspout is a product of that specificity, a manifestation of universal atmospheric physics in a particular and unprecedented local form. Understanding it completely will take time and continued observation, and the gradual improvement of the tools that meteorologists use to study phenomena like this. The full scientific story of May 2nd is not yet written. The paper is not yet published. The models that will eventually be run to reconstruct the event have not yet been configured. The understanding that will emerge from all of this will be more complete than the understanding that exists right now, which is itself more complete than the understanding that existed before the event. That incremental improvement of understanding year by year and case study by case study is the texture of scientific progress in a field like mesoscale meteorology. It does not announce itself with dramatic revelations. It accumulates quietly, the way snowpack accumulates on a mountain over a long winter, each individual storm adding a small amount, the aggregate becoming something substantial that shapes everything downstream. The Wenatchee Mountains know something about that, about the slow accumulation of something that eventually matters, about the way small additions to a growing system can eventually change the character of the whole. What the mountains showed us on May 2nd was small, a narrow column of rotating air, brief and unrepeated, documented and verified and entered into the record. Small enough to be a footnote, large enough to be a first. And in the science of understanding what the atmosphere can do, first have a way of resonating forward in time, shaping what comes after them, opening possibilities that the record before them kept closed. The tornado that was not supposed to happen happened. The mountains showed something new, and the sky above them, vast and patient and full of things we have not yet seen, continues to move in the ways it always has, holding its other secrets until the day the conditions are right and someone is watching.